So this session is on enabling the future of fusion energy and the role of the elastic fabric adapter. My name is Faraz Ahmed, and I lead AWS's Net Zero Electricity Program, which is part of Amazon's wider goals to be net zero by 2040. I have over 18 years of experience in the energy sector across industrial technology development, project development, and energy procurement and implementation.
And I'm Sam Frank. I'm a senior scientist at Realta Fusion, and I have a PhD in plasma physics, and I've been leading the development of our high-performance computing resources on AWS.
The objective of this session is to provide an overview of the current state of nuclear fusion, the potential it has, and how AI and computing can accelerate the development and commercialization of this technology. So in this presentation, we're going to cover 4 items in the agenda. First, we'll provide an overview of what nuclear fusion is and how it fits within the broader energy transition. Secondly, we'll present on how cloud and AI can accelerate the potential of nuclear fusion. Third, Sam will present on the role of the elastic fabric adapter and how Realta Fusion are using AWS resources. And finally, we'll close on how we can all enable this future together. So to provide some overview and context on where we are on this energy transition, it's quite clear that the world is clearly off track at 1.5 degree scenario. And we're at a really critical moment in the climate change imperative. However, there are a variety of zero-emission electricity sources available. For wind and solar, we've experienced a massive deployment and cost decline of these technologies. Today, 12 to 13% of all electricity generation today is from wind and solar. That number would have been unimaginable 15 years ago, and is a testament to the deployment and the progress that we've made. In the center here, we show energy storage. Energy storage includes technologies like batteries. In 2023, there were over 45 gigawatts of energy storage deployed. That's more than double the amount the year before. And on the right-hand side, we're showing geothermal and nuclear fission. And these are really important because they can provide the base load power that the grid needs. Geothermal is where we drill into the earth at depths. And at those depths, there's a heat transfer that can occur where we transfer the heat into warm water, generate steam, and drive electricity. For nuclear fission, we've been deploying this for several decades. Nuclear fission is based on taking an atom and splitting it into its multiple constituent elements. By splitting the atom, this generates energy, and the heat is then used to warm water, create steam, and drive electricity generation. All of these zero-emission electricity sources are important because the ultimate goal we're trying to achieve is a reliable, affordable, decarbonized grid. And this is important because electrification is the key decarbonization pathway for the economy. By electrifying, we can ensure that we have the potential to create a lower cost and lower emission end-use application as we substitute fossil fuels. This could be electrifying heat, electrifying transport, and electrifying industrial processes. At the same time, as part of the energy transition, we are going to see the increase of electricity demand, and it's important that we have generation sources that can keep up with this demand as well. However, the key thing I want to emphasize here is that nuclear fusion is different. Nuclear fusion is not about splitting atoms, it's about fusing them. And it's also still very nascent and in the early stage of commercialization. But it's a potential game changer here because it provides the promise and potential for abundant, emissions-free energy. The visual here is describing what is actually happening at this fundamental atomic level. You've got 2 atoms here, both hydrogen. One is deuterium, which is a hydrogen atom with 1 proton and 1 neutron. The other is tritium, which is 1 proton and 2 neutrons. And when these fuse together, they can produce helium with 1 additional neutron. And the way I like to describe this is that essentially we're trying to build a star on Earth. We're fusing lighter atomic nuclei into heavier ones, converting matter into energy. This is made famous by the equation E equals mc squared. E equals energy, m is mass, and c is the speed of light. So by using this energy is the same energy with which a star is kept stable, with gravity pulling it inwards and the energy from the fusion reaction keeping it stable. There are really 4 fundamental characteristics of nuclear fusion that makes it a game changer. First, it's emissions-free, as I mentioned. So it doesn't produce the greenhouse gas, the carbon, or the methane emissions that we know is driving the climate change agenda. There's no nitrous oxides, no sulfur dioxides, because we know that these pollutants interact with water and other environmental molecules to create acid rain, which harms plants, trees, and wider ecosystems. And these pollutants are also harmful for human health because they harm the human respiratory system as well. Nuclear fusion promises fuel abundancy. So the deuterium is readily extracted from water, and the tritium can be generated through lithium. It can provide the baseload power that we need, continuous, non-intermittent energy production that is not dependent on the weather. And finally, in terms of safety aspects, there's no risk of a chain reaction. As I described with fission, where you split the atom, which produces neutrons, which then further on goes and split other atoms. With fusion energy, we're fusing lighter nuclei into heavier one, and it's that reaction that's producing energy. There's no long-lived radioactive waste as well, so it's a simpler aspect to manage. So to state the obvious, we still have not achieved a commercial, cost-effective fusion machine. And there's the perennial joke in the energy sector that fusion is always 10 years away. But I want to show you here on the right-hand side on this chart that we are actually making progress. The blue area is what's needed for a commercial power plant, and we've been making steady progress over the last few decades. In fact, it was quite mind-blowing to me that we're now within approximately a factor of 2 to get to where we need to be. And also, progress is accelerating. We've got over $7 billion invested to date in private fusion companies, all in the last few years. We've now got 16 public-private partnerships globally, trying to focus on making further progress. So this surge has created a diverse approach, what I call a many shots of goal, to try and ensure that we're increasing the likelihood of identifying a commercially viable solution. But the rate of progress has basically been limited by empirical science. So what I mean by this is that we build, we test, we then generate data from these machines, we then iterate and scale and simulate, and we continue that incremental progress. But the rate here is really taking years to decades, and that's the problem that we're trying to accelerate. The good news is that AI is offering new possibilities to accelerate this progress. So how can cloud and AI accelerate this nuclear fusion potential? So with AI offering new possibilities to accelerate commercialization, AWS supported an independent report from the Clean Air Task Force. The Clean Air Task Force is a non-profit committed to advancing clean energy solutions. And their report studied how fusion energy and AI is complementary and can drive further progress. They identified 2 main pathways to accelerate progress. The first is around empirical scaling through simulation, so minimizing prototypes by ensuring that we're making the right simulations with higher fidelity. And secondly, improving the iteration and making sure that we're driving development as quickly as possible. There were 5 challenges now associated with nuclear fusion, and AI is helping all of these in substantive manners. And I'll go through each one of these. The first is on material selection. I remember at university, one professor of mine always said that the rate of human development and engineering development has always been limited by materials, and nuclear fusion is no exception. So AI is being used to predict materials behavior and forecast anomalies. These materials need to withstand high thermal gradients, high amount of radiation, and high amount of neutron bombardment. In order to create the conditions for nuclear fusion, we need superconductors, which just simply means we need to be able to conduct electricity with zero resistance. That's normally only been able at extremely low temperatures. But now we're able to do this at higher temperatures, and AI is being used to enhance the process control as well as the quality assurance in these manufacturing processes. In terms of the inertial fusion energy, what this is describing is the conditions required for the fusion energy reaction, where AI is being used to ensure that the lasers used in that are accurate and powerful enough for the right conditions. And on fuel, on the tritium, which I mentioned at the beginning of the presentation, tritium is not naturally prevalent, so it has to be man-made. We create that by bombarding lithium with neutrons. But we want to maximize the ratio of this tritium breeding and ensure that we're doing this in the most cost-effective way. And finally, on advanced diagnostics and control, magnetic fusion reactors need to control the plasma, and AI is being used to predict the instabilities in order to better control them. So once we've actually got, hopefully, a fusion reactor being produced sustainably, what we also want to do is to drive the commercialization. And to do that, we need to make this more cost-effective and ensure that we're reducing the levelized cost of energy. I want to talk about two main ways that AI can do this. The first is on maintenance. And ensuring effective maintenance is key because by minimizing the downtime, we can maximize the energy output, which obviously reduces the cost of that. Predictive maintenance is really key here because there are three main areas that it can be helpful. The first is on forecasting anomalies. Secondly, on predicting the amount of useful life. And third is on diagnosing the particular faults that are occurring. An example of this is the East Tokamak reactor, which is actually using predictive maintenance to predict vacuum leaks before they occur. And in terms of maximizing the energy output, we want to optimize the heat exchangers so we're getting the maximum amount of energy output into commercial systems to drive electricity and other applications. But one key point I want to mention here is AI and fusion are symbiotic, where each one drives mutual development. AI can help to advance nuclear fusion energy, and nuclear fusion energy can provide the carbon-free energy needed to ensure that AI and computing are deployed in a more rapid and sustainable manner. So these are not just conceptual ideas. These are real-world applications being used today. Developers are already using high-performance computing to run high-fidelity simulations to understand how these machines can operate and minimize the need for physical prototypes, and that also accelerates the progress and development. AI is being used to address the uncertainty and risk, and critically to quantify this so we can assess the potential of wrong turns and ensure that we're avoiding these costly wrong turns. And Realta Fusion is a real example of a company which are using these applications of computing resources to accelerate fusion development. They're the first company to use AWS cloud computing for simulations to enable fusion device design. And I'm going to hand over to my co-presenter Sam to discuss how they're using it in real-life examples today.
All right. Thank you, Faraz. And now we're going to get into some nuts and bolts of how we use high-performance computing on cloud resources like AWS to advance fusion, and what we're specifically doing at Realta Fusion. So Realta Fusion is a magnetic fusion energy startup that was spun out of the University of Wisconsin, and we're based in Madison, Wisconsin, and we use something called the magnetic mirror to generate clean fusion power. So a cartoon of the magnetic mirror is shown on this slide here on the right. What a magnetic mirror does is it holds a plasma, which is the hot hydrogen gas that you fuse together to make helium, in between two big magnets, which are shown in orange here. When the plasma is held in between those two big magnets, there's a magnetic field well that the plasma bounces back and forth between the two magnets in, and this bouncing back and forth is called mirroring, hence the name magnetic mirror. So we like this concept because it's simple to build and can quickly be deployed to help decarbonize electricity with fusion. And This isn't merely something that's a cartoon on a slide. We have an actual magnetic mirror that we work on with the University of Wisconsin called WHAM, the Wisconsin High Temperature Superconducting Axisymmetric Mirror, which recently got its first plasma this year, which is shown in that video that just played there on the slide here. And to emphasize how simple and quick to build and deploy the mirror can be, WHAM has the strongest magnets that have ever been used in a fusion device, and from magnet delivery to the device turning on took only 14 days. In fact, this is a major milestone for fusion research in general, since the magnets used in WHAM are the strongest steady-state magnets in the world at 17 Tesla, which is about 6 times what a typical MRI machine has. And they are the strongest magnets ever used in a fusion machine in steady state. So the mirror is not without problems, though, and one of the biggest problems is that the mirror can be unstable to a certain plasma instability called the interchange mode, which is shown here on this slide. What the interchange mode is the plasma bulges out from in between the magnetic field lines and eventually escapes. You can think about this with the analogy of if you try to hold a piece of Jell-O using a set of rubber bands. Even if you squeeze it more tightly, the Jell-O still slips out. So the way we actually stabilize this in the experiment is we use advanced stability actuators. These include things that spin the plasma, which we'll see in a moment. And it's incredibly important to use simulation to help design these actuators and effectively deploy them in the experiment. So this is an example of a simulation of a plasma in our WHAM experiment that is simulated using this technique called particle in cell, which we're going to get to the exact details of what this is and how this algorithm works in a moment. So the interchange instability, you can see here, causes the plasma to go from this initial nice column. It's sliced down the middle of the machine, so it's a big sausage of plasma, and we're looking at just one slice in the middle. And it spins around and eventually goes out and hits the wall. We don't want that because if the plasma isn't confined, it's not doing fusion. So what we can do is spin it around. And you can see in this simulation where we've deployed a stability actuator, the plasma stays in place and is nice and stable. So this really demonstrates how simulation is key to understanding and then preventing instabilities. So let's get into some more details about how PIC works and why we need HPC and have to use resources like AWS to simulate these things. So what I'm showing here is a very simplified model of our plasma. It's just some particles in a box. And a plasma is made up of 2 different kinds of particles, ions, which are typically hydrogen, and electrons. So if we wanted to simulate this, what's going on in this box, these charged particles interact by long-range forces called Coulomb interactions. And if you want to simulate this how it happens in real life, you would have to tally up every single interaction between every single particle in the box, and then advance them for some amount of time, and then redo this tally. This is completely computationally intractable. You can show with mathematics that this would take the biggest computer in the world 1 billion years to do a realistic problem. So we have to use a trick, and the trick is the particle in cell technique. So what we do is we divide this box up into something called cells, where all the particles live in some cell. And then we, instead of computing how each charged particle interacts with one another, we deposit the currents or the charge from those particles onto the cells, and then use those cells as a computational grid to calculate the fields associated with those charges and currents. So you can calculate the electric and magnetic fields, which we show with the blue lines there that go along the grid. This is just an example. It's not totally realistic to what these would be in real life, but it's to give you an idea. Then once we have these fields, we can move the particles around by calculating the force that those fields exert on the particles, and they get pushed. So the electrons get pushed in one direction by the electric field, and the ions get pushed in the other direction because they have opposite charges. And from that push, we can advance in time and move the particles and repeat the algorithm. And this algorithm has been shown and used for a very long time. It was actually originally invented in the 1920s, very shortly after plasmas were discovered, and before computers even. And you can use this to simulate basically the dynamics of any plasma that you're interested in, such as plasmas in space, or in our case, in a fusion machine. The thing is, PIC, even though it's a very old algorithm, is still able to push the limits of computing. So in a real simulation of something like WAM that we showed earlier, you need hundreds of these grid cells in 3 dimensions, not just the 2 we have in this simple example. And to eliminate noise, since this is effectively a Monte Carlo technique, you have to use lots and lots of particles. So a realistic PIC problem, like the ones we showed, typically requires thousands of processors and very large amounts of memory to efficiently run it in any reasonable amount of time. And the way we actually utilize all these processors is we do something called domain decomposition on the problem, where we split the problem up and we say each processor gets this part of the grid. So here we split this PIC grid up into 4 different domains. And what would happen if you were to evolve this algorithm on these 4 domains with 4 different processors is each processor would advance the particles, deposit charge onto their grid, communicate with the other processors on where the charge is on the grid. They would then solve for the field, then advance the particles, and then communicate again to where the particles went so that all the other grids and processors know what's going on at a different point. This is important because these particles are interacting through long-range forces, so you need to have this communication step. The problem is that this communication is very intensive because you need multiple communications per time advance, and in a realistic problem, you do tens or hundreds of thousands of time advances to get a full simulation. This can result in the problem being something that we call communication bound, where rather than being bound by the actual computation on runtime, more time is spent with processors communicating between one another than the actual computational steps. And the solution to this is you need a fast communicator. So in many modern supercomputing infrastructure, a lot of time and energy is spent making sure that all of the different processors in that supercomputer can communicate together very quickly. So Realta wanted to run large-scale PIC problems on the cloud so that we could effectively utilize our experiment and do the best physics possible on the shortest timescale possible. What this meant is we wanted to replicate what was possible on large government-sponsored supercomputers with AWS. The reason why you might not want to use a large government supercomputer is to get time on a large government supercomputer, you typically have to write a proposal. That proposal sits in review for 1 or 2 months. Then you get the results of your review. They give you some amount of the time that you asked for, and then you have to wait another month or 2 for that time to become available to you. In a startup, 4 months is a lot. Much more so than it is in academia. And it's very useful to have a resource where you can just say, I want to put down a credit card and do this simulation right now. Another thing is, when you're operating on a government supercomputer, you often don't have rights to proprietary information that could be generated or is held on that supercomputer. Everything has to be done in an open science fashion. Realta often does open science. However, we want to keep the option to protect our IP as well. And cloud services like AWS enable that. So we submitted to do this as a proof of concept, running a PIC simulation on AWS by building a supercomputer in the cloud for a proposal on the Compute for Climate Fellowship. This fellowship is organized by AWS in partnership with the International Research Center for Artificial Intelligence, IRCAI, which is under the auspices of UNESCO. And what it does is it gives startups like us at Realta the resources and support needed to build a proof of concept that advances a revolutionary climate tech on AWS. So we applied and we were in the inaugural class of this fellowship, and we went forward to go build this PIC application on AWS for the first time. And the way we did this is we utilized something called the elastic fabric adapter. So as I mentioned, PIC problems are very communication bound. So you need to take advantage of technologies that allow you to communicate very quickly between many different processors. On a typical high-performance computer that you'd see at a government-sponsored supercomputer, they have a custom-designed interconnect that connects all of the cores on that supercomputer together. And it's highly optimized for that specific machine. Until very recently, with the advent of the elastic fabric adapter, a comparable sort of interconnect for cloud computing services did not exist, and you could not do large computationally bound, communication bound simulations on cloud resources and match the performance of government and other large site-based supercomputers. However, the elastic fabric adapter by AWS has completely changed this. So what this is it is a clever technique for communicating between all of your different processors that you have in your cloud, such that communication can be done quickly and efficiently on variable cloud architectures. So it uses a couple of tricks to do this. The first is it bypasses the operating system. So normally when you want to communicate between two different computers, it has to go through the operating system and the TCP/IP stack and then go out to the overall network and talk to the other computer and go back through its TCP/IP and then through the operating system. Elastic Fabric Adapter gets rid of that. It says we're going to bypass the OS and allow things like direct memory and GPU access, which are this GPU direct and RDMA that are shown on the slide there. So this cuts out one piece of latency from the step. Furthermore, it then allows you to do out-of-order communications over the network, which allows you to account for network instability and traffic more effectively so that you don't end up with enhanced latency if there's congestion on one part of your cloud network. And this enables you to get consistent and fast performance that is as good as a classical supercomputer interconnect on a cloud-based system with a more flexible configuration. And the great thing about EFA is that you don't have to change anything in your code base to use it. You just simply need to load the correct lib fabric, which is this underlying networking fabric that the EFA uses, enabled MPI, which message passing interface, which is a bog standard parallelization tool that's used in many computing codes, and compile your code and it'll work. So what we did in our proof of concept is we took AWS and we built a parallel cluster utilizing a high-performance file system with FSX, EC2 HPC7A instances, which are 192 core instances that you can run on Amazon, and then we connected them all up with an EFA. And this allowed us to replicate the capabilities of the computer we showed earlier, Perlmutter, which is located at Berkeley Lab, and do so on the cloud. So a sort of simplified look at the system architecture is here. It works very similarly to any typical cluster or supercomputer you might be familiar with, except everything is operating on the cloud. So we have a head node that you log into through some sort of remote login portal, such as SSH. And from that head node, you can build your software stack on your high-performance file system. And then when you're ready to actually do a simulation, you take the software stack on that file system and you submit a job using that software to your compute nodes, which are spun up dynamically. And these are typically, in our simulations, HPC7A, EC2 compute nodes that are connected with an EFA interconnect. Those run your simulation, output your data to the FSX file system, and then when they're done, they're spun down, and you have your data and you can do whatever you want with it. For example, put it in an S3 bucket. So we were able to quickly get our software stack up and running and highly performant on this cluster that I just showed. So within about a week, we had a benchmark running that showed we had performance that was actually 10% better than the Perlmutter supercomputer we had previously been using. And this was using a vPIC, which is our PIC code software stack that we had built from the ground up with a libfabric compatible MPI. So what we did with this, once we had the initial benchmark going, is we said, well, we've still got credits left. Let's do a trophy shot and really show that this proof of concept is something that we can extend all the way to production cases. So that's what we did. And we did the simulation you see here on the screen. So this simulation was run on our AWS parallel cluster. And it shows a WAM experiment where we were interested in looking at a particular instability, and we wanted to simulate it with PIC. So we did a PIC simulation on 1,200 cores that were connected over an EFA, and this ran for about 1 week to make the movie that you're seeing here. And with this, we actually are doing real science that we are using to improve our experiment. And this is a key thing to Realta's overall business strategy. One of our big advantages is we have an experiment that can run hundreds of experiments per day, WAM, shown there on the right. And from those experiments, we learn stuff. We say, hey, this worked, this didn't, we saw this instability, this actuator worked well, and we want to understand it better. And using tools like AWS, we can rapidly iterate with that experiment and do a simulation on something we saw one day, and then within a few days have a result that says, hey, here's what was going on here, here's how you can improve the experiment, and feed that back onto the hardware. And having tools like AWS where you can deploy these things quickly and effectively is incredibly important to us. So that's all from me for now, and I will hand it back to Faraz to close us out.
Thank you so much. It's really insightful when you see these real-world applications actually being used. So thank you for that, Sam. So in order to close, I'm just going to summarize with a few key messages. Given that we're at such a critical moment in the climate change imperative, nuclear fusion really could be the potential game changer that we need for the abundant, emissions-free energy that the world is needing. All of these developments across high-performance computing, AI, and nuclear fusion are really symbiotic, where development in one can drive development in the others. And that's something where we get a positive feedback loop as well, where AI can actually accelerate the development of nuclear fusion, and nuclear fusion provide the carbon-free energy for deployment of AI and computing. AWS provides the tools, the resources, and all the capabilities required to run simulations for our customers like Realta Fusion who are using this to address their challenges today. And this is an opportunity for everyone in the computing and AI sector to really engage on one of humanity's grand challenges, which is on securing our energy future. So here on this slide, I've posted several links for you all to engage further. First, on the left is a link to AWS Parallel Cluster, where you can engage on some of AWS capabilities here. In the center is a link for a primer on fusion energy from Stanford University, where you can understand more of the fundamental science. And on the right-hand side is a link to Realta's development and the background that they've been doing there. So thank you so much for this opportunity to present to you on this exciting topic. We'd love your feedback. Please put in your feedback and complete the survey in the mobile app. And we've posted our contact details as well if you've got any follow-up questions. Thank you so much.